Hello. Might as well get started here. It looks like folks have come in. Welcome, everyone. I am Charles. I work at Weights and Biases. I'm a deep learning educator, which means that my job is to both, one, sort of teach people about deep learning and how to use it, and two, to teach people about weights and biases and how weights and biases can make your deep learning pipelines run better, more efficiently. So what we'll talk about today, I'll do a little bit of intro and background on weights and biases, then talk about some of our features, weights, biases, dashboards, and artifacts, and then close out with a little interactive demo of training a raccoon detector using weights and biases and our integration with the YOLO v5 library. So as I'm going through this, I welcome folks to post questions in the chat to try and make this, as interactive as possible. I want to be able to answer any questions that you have. So Weights and Biases is a San Francisco-based startup. It was founded originally, one of our co-founders, Lucas Biewald, was working at OpenAI, found that the sort of way experiments were being tracked and like information from research teams was being sort of collated and integrated was, people were using things like, Word documents and Excel spreadsheets, and he saw an opportunity to make a tool that could unlock a lot of potential additional developer productivity that was being left on the table. So he had previously worked on some data labeling startups to sort of improve that first part of the machine learning pipeline, and with weights and biases, the focus is now on the rest of that machine learning pipeline when you go from data to models. And so I think the question that sort of I use to kind of motivate like why weights and biases is important is what are the best practices for organizing our machine learning projects. There's a bunch of ideas out there for how to organize software engineering projects. There's tools like Jira, there's GitHub, there's continuous integration tools like Jenkins. There's all these best project practices out there, and if you look around, you'll find information about them for software engineering. ML engineering is actually quite different. So what are those best practices? And when I first asked myself this question a couple of years ago when I was in graduate school studying neural networks, the answer was basically that it was the Wild West. There were, no one had set down best practices. There were some people trying out some things, but there were no clear ideas about what those best practices were. So weights and biases provides a system of record for machine learning experiments, and is in some ways a sort of a new sheriff in town for the Wild West. So the three guiding principles for weights and biases here are in designing this system of record and in designing these tools for implementing best practices in machine learning are reproducibility, visualization, and quick integration. So by reproducibility, I mean all the things that you need in order to be able to recreate past experiments or past models. Lineage, version control, registries, and saved information, all that kind of stuff. By visualization, I mean that instead of just saying, oh, I want to store all that information and have it in principle accessible or programmatically accessible, the like guiding principle for weights and biases is that the experience of working with that information should be visual and intuitive, in addition to being programmatic and sort of like programmatically accessible and configurable. So we provide things like live dashboards where you can quickly experiment with things in an interactive way. We provide tools for sort of visual collaboration, and for sort of managing which analyses and information are visible to which members of the team, and which are sort of shared out more broadly to the broader community of stakeholders or the academic or industrial research communities. We also, in designing all these things, one of our core sort of guiding lights is that we want this to be done with quick integrations, being able to like really easily add weights and biases features and superpowers to your machine learning pipeline, with modular solutions rather than sort of like locking you into an entire platform then solving all your problems for you. But at a price. And this is something that was built out of our sort of partnership with leading research institutions, where we sort of started with folks like OpenAI and Toyota Research Institute. This is what those teams told us they wanted, and we found that is what most machine learning engineering teams want: modular, interoperable solutions. So in addition to being sort of modular and interoperable, we're also agnostic to which framework you wish to use. You can use whatever framework you want. If you're using certain specific frameworks, will already be built into it. If you're using PyTorch Lightning, we'll see later with the YOLO v5 object segmentation framework, we're integrated there. Hugging Face for natural language processing. We also have special tools for logging things nicely in even low-level frameworks like PyTorch and TensorFlow. And you can do this all in an environment agnostic way. Excuse me. Like, we aren't going to tell you have to run everything on Google Cloud or Azure, because that's what we like to run our stuff on. And you can also sort of log the information and track your runs either in either locally to your own on-premises compute, to somewhere in the cloud where you'd like to store it, or to our centralized servers. So it's sort of plug and play and configurable. So we offer a lot of several different modular tools, several different solutions to different problems in the MLOps space. Experiment tracking, registration of models and datasets and other large files. We also offer tools for hyperparameter optimization and for collaborating and providing reproducibility information. But I'm going to focus primarily on the experiment tracking and the model and dataset registry stuff in this talk. So the weights and biases provides a solution to a problem that I tried to solve myself when I was in graduate school, when I was a PhD student. So this is actually a real image from the notes that I took when I was doing my dissertation research on neural network optimization. I was just sort of writing notes down into this Google Doc, like, in a way that at the time made a ton of sense to me, but now like kind of does not anymore. And that was always like very difficult to communicate with other members of my team. So I had the information. It was better than what I was doing before, which was trying to keep it all in my head. But it was not something that was scalable across time or across a team. So the alternative that weights and biases provides to that sort of like Google Doc or spreadsheet approach to tracking experiments is basically a database of information about your runs. So you tell us information about your experiments as they're going, and we store them in a database for you that you can then later go and interact with to like pull insights out of. So the idea here is maybe like log as much information as you can. Just log like every piece of information that's thrown off by your ML experiments, and then come back later in this interface and pull the insights out of that information. So you can interact with this like just by heading to a URL, whether that's a URL pointing to something on your local network, or in the case of logging into our public cloud, a public URL that's maybe behind, you can control access. So not everything has to be done completely in public, just like with GitHub. But this particular project done by my colleague Stacy is a public dashboard, so anybody can come and take a look at it and see the machine learning experiments she ran and sort of like dive into them. So I'm going to go ahead and take a look at that. Andrea, if you could share the link to this in the chat there. So this is that weights and biases dashboard here, which basically gives a sort of visual way to interact with this database of information about Stacy's experiments. So on the left-hand side is the sort of like tabular view of the information about all the experiments Stacy did as part of this project using Berkeley's Deep Drive dataset to do segmentation, to train a network to do segmentation of images. So on the left-hand side, each row here is one run, one experiment that Stacy did, and the important metrics for that run. So what was its overall accuracy in identifying the classes of the segments it was pulling out, and what was its accuracy on a particular set of classes, the traffic classes. So this is a sort of like compressed summary of the information that has been logged. You can also sort of pull that table out and see all the columns in that table for all these experiments, including little notes that Stacy left for herself, and maybe some tags that she's added that could mean that could be used for organizing your sort of like ops pipelines. Some models can be tagged as maybe production ready, some as maybe candidates to become production ready, and these tags can then be sort of programmatically accessed in order to determine which models flow from a training pipeline into actually being used in production, or which models in production maybe need to go back and be retrained. So all that information is here, both visually accessible to anybody taking a look at this interface, or programmatically accessible. And then along with that kind of sort of human applied metadata information, there's all kinds of hyperparameter information here. Stacy was trying out a whole bunch of different potential hyperparameter choices for this segmentation task. So we don't just have that like numeric and text data here. We also have, let me maybe zoom out a bit to make that easier to see. We also have rich media objects, interactive media objects associated with all of these runs. So here are some inputs, predictions, and the ground truth targets for several runs that Stacy's picked out as particularly important. And these are now associated directly with the runs, and I can take a look at this rich media output, and I can also click through and check out the details for the particular run that produced that output. So just taking a look at this here, maybe what I want to do in this section is focus in on how models are doing on people. This is an important component of any sort of self-driving pipeline. You want to know how well your model is doing looking at specifically this sort of pedestrian class. So I can actually interactively decide which pieces I want to see, which components of this segmentation mask I want to look at, and sort of focus in here on this person and sidewalk class. So first, I can see that the model has incorrectly identified a sidewalk. This sort of crosswalk here is incorrectly identified as a sidewalk. That's bad news for a self-driving car. You don't want to drive on sidewalks, but you can drive on crosswalks in the right situations. And also, we can see that the model has failed to identify two pedestrians in the back of the image here. So these two in the if you look very closely at the ground truth, there are in fact two pedestrians in the back. Very difficult to see from the images. Maybe not surprising that our networks are missing it, but they are in fact missing it. Not doing a great job pulling it out in the back there. So that's something, maybe we can identify this as a hard example, as one of those, an example on which a lot of our networks fail. And so networks that go into production maybe should always do well on this image. This is a like a unit test, I guess, for our networks. So being able to interactively check out this sort of rich media and weights and biases is something that can help improve your overall sort of quality of models. Like in principle, that information was always there, but it's much easier to find if you've like logged it into a nice interface like this one. So we were looking at sort of like the level of the entire project there. So many runs. You can also drill down and check out a specific run within and look at the details of a particular experiment or a particular model training. So here we have the information for one particular that the model I was just looking at that was missing those pedestrians. I can see how its metrics changed over time. These like training metrics, like the score on the intersection over union for those segmentation masks, and the accuracy for identifying different classes. I have even more of those nice. I can actually watch how those the predictions of the network evolved over time. Drop the ground truth and focus just on the predictions here. So I can see that actually that error with misidentifying the sidewalk sort of pops up early in training. So that can maybe help me identify places where I can intervene to prevent models from developing bugs or mistakes. There's also a ton of rich information associated here with this particular run. So information like the gradients for every single parameter in the network throughout training, really useful for debugging. And even if you don't need to look at them at the time that the training run occurs, maybe later you recognize that some bugs snuck in and there's signatures of them in the gradient information. That's something you can then access later. In addition to this kind of very ML specific like model training information, we also will automatically capture for you a bunch of relevant information for performance and for reproduction of experiments. So in this system tab here, I've got all the system metrics from Stacy's machine as she was running this this particular run, how much of the CPU were we using and the memory, how much of the GPU were we using. This can help me determine maybe if I need to make optimizations to a particular model when I go from training to inference, or which particular chips, how much GPU RAM am I going to need to run this the same way it was run during training. Looks like she was using 100% of the GPU. So like the GPU was really like we were at almost 100% memory allocation. So if we're going to run this model in production, we're probably going to need an equivalently powered GPU. And if so I can also find out information like which GPU was that she was running it on. If I head to this overview page, which has like things like Stacy's notes on it, it also has a bunch of automatically captured information, like which computer she was running this experiment on, and like extremely detailed information necessary to like sort of recreate this run. I think there's a requirements.txt file, for example, that's been captured in another tab. On top of that, we also capture any Git information. So this was based on a GitHub repository, and so there's a link to the GitHub repository. But maybe if you just knowing the repository isn't enough, repositories change over time. So we've also got a specific pointer to the particular Git commit that this model was run against. And there's a nice little command here to recreate that Git repository in the state that it was in that particular commit. And even further, not every person sort of does a commit before every single run. And so that Git commit state might not accurately reflect what code was available at the time that the sort of state of information at the time that the run was created, so that Git commit might not be enough. But we also capture for you a diff.patch. And this is all the information you need. You can apply this with a simple git command. You can apply that patch and get the exact state that everything tracked in Git was in when this run was run. And there's that requirements.txt file for recreating the environment. So all this information is grabbed automatically and associated with the run in a way that you can trust. As opposed to just what people's sort of notes said they were doing or what their recollections were. So just some other quick things. We also capture things like the standard output. We'll grab your code for you if you want. If you're using Jupyter notebooks, we'll have the exact state of the Jupyter notebook available in online. I think this diff.patch, for example, actually has the Jupyter notebook state in it for this particular example, including, very tiny details like how many times each cell had been executed, and the specific sort of JavaScript outputs of each cell. All that stuff can be recreated, and so you no longer have to worry about losing track of this stuff. And this has really saved my bacon multiple times when working on projects since joining Weights and Biases, where I've like lost track of the state of a Jupyter notebook or accidentally deleted something or a cell or a script, but that information was there in Weights and Biases to save me the trouble of having to rewrite it or attempt to recreate it. So that's what our sort of dashboards provide there, all that information in this interactive form. And then one last quick point about that. We were just looking at Stacy's version of that collection of experiments, that project. She has her own view on that database of information, but actually every single one of my coworkers who's taken a look at this project has their own view. So I have my own personal view. where I took a look at some of the sort of hyperparameter optimizations or the hyperparameter optimization process, and have like a nice little panel here that pulls out information about which hyperparameters had the greatest influence on the final metrics. Which ones had the most influence on the overall sort of accuracy for identifying which class a particular like pixel came from, and which models did, or which parameters had the most importance for determining performance on that critical pedestrian identification subtask. So all that information that's recomputed live on the fly. You can come up with new analyses that you want to do. You could say, oh, I want to focus on the ones that had really high performance on the overall metric, but really low performance on the on the human subtask. Which models were those? What? And you can dive into the causes there. And I can do all that despite the fact that I wasn't there when these experiments were run. And like I can just find all that information and create those analyses myself without having to have been the one who did it. So that's what our this like experiment tracking and dashboard tool provides at Weights and Biases. There's lots of things that you can do with that, and there's a little bit more detail here that you can find if you check out the slides. Actually, Andrea, if you could share a link to the slides in the chat, that would be great. But I want to make sure we move on and get to our the interactive raccoon detection demo at the end. So the focus there was on like information about models, information about the compute, these sort of like relatively small things that you might track that are on the order of maybe like megabytes per experiment. There's a bunch of other information that gets associated with runs. So data sets, like gigabytes of data organized into data sets, and the actual model files, which can run into the hundreds of megabytes or more. All that information, it's difficult you want to be able to version control that information, but it's difficult to do that using something like Git that was designed for versioning source code. So Weights Biases provides a toolkit for doing that. I ran into this same problem when I was doing my experiments in my PhD. I needed to, move data, like results of experiments from one computer to another. I wanted to be able to run analyses and associate them directly with the data that they were run against. And so I built this like janky pipeline for doing that out of Dropbox, which eventually kind of like collapsed on me shortly after my dissertation was published, and ended up deleting a bunch of my data. So that's definitely, trying to roll your own here is a very dangerous thing. So the tool that Weights and Biases provides for this is called Artifacts. And it allows you to associate large binary files in a version-controlled way with particular runs that consume information, like runs that take in data, and things that are produced by runs. So models might be produced by runs, and we associate this with your projects in a nice, again, sort of like visual way, in addition to like a programmatic API-based access. So on the top here, we have a little graph representing a particular pipeline from a colleague's project training I think it's a BERT model, but training a natural language processing model fine-tuned on tweets to mimic particular Twitter accounts. So I can actually follow, using this graph, the blocks here, the square nodes in the graph are jobs, are runs, and the circles are binary files, are artifacts, are information produced or consumed by runs. And I can click through this in the Weights and Biases interface to check out which runs produced which particular artifacts, which particular say data sets in this case, and how those were consumed. And then this all has like rich metadata and all the information associated with those like large objects, and in a version controlled way. So if somebody comes along and re-downloads this from the same Twitter account to like fine tune a second time, or to update to prevent model drift, I'll be able to see that in this artifacts interface and track that. And then, in addition, if you log your information in the form of a weights and biases table, we provide tools for like drilling down into like a complicated artifact, like a data set, and pulling insights out of it. So not just the interactive dashboard that I showed you before, but an interactive approach to doing and sort of data analysis on things like the inputs and outputs of your model. So that's in the top left here. I have an example on the MNIST handwritten digit classification data set. I took a table of inputs and outputs for a particular network and then applied a group by operation inside weights and biases to find examples where my model was incorrect in what it guessed the correct label for a particular example was, so that I could maybe sort of start to debug what's causing my um, what's causing my network to make mistakes. So looking here, I can see that there's my network is learning some maybe the top row here shows the network's mistakes where it guessed 0, but the actual true label was something that was not 0. It looks like maybe my network has gotten a little over enthusiastic about identifying sort of closed loops or circular shapes as zeros. So there's a lot, you can see there's a theme of like circular shapes here in this top row. So that can maybe help me debug my models. It can also help me debug my data set. If I look in the 4th row here, where the model was guessing that it was a 3, there's some interesting patterns about the model's performance, but also check out this particular input image here. Like that is, I don't know what the true class of that is. I think 3 is a good guess, but clearly there's something wrong with my data here if this is something that I'm asking my network to make correct predictions on. So this can help you get insights about your data and about your models, whether that's image classification. This is a style transfer example for audio, and then more complex image tasks and classification like segmentation. So that like interactive interface with the segmentation mask that I showed you plays nicely with this analysis tool. So there's a question. I see in the docs that artifacts can point to other outside sources. Can this easily interact with DVC or another data versioning system like that? I think the answer to that is yes. You can definitely use it to use, like if you have your information stored in the cloud somewhere, then you can sort of point to that information and you don't have to store it with us, though we do provide 100 gigabytes of free storage. If you're using DVC to version stuff, I would say that you wouldn't necessarily want to both version stuff with DVC and version it with weights and biases. But this like this like data set interrogation toolkit here, this DSViz stuff, is sort of, it uses artifacts, but it's separate from versioning. So you could version your stuff with DVC, but analyze it with weights and biases if you wanted. So that's part of the sort of like modularity of these tools. So these bring a lot of benefits in terms of being able to track and monitor data set changes and changes in models, connect those things to each other, create a single source of truth, and also to be able to distribute stuff. So you can log, store, and distribute large binaries. So it's something that I use a lot when I need to get data to people. So like maybe I'm running a public class and I need to get 2 gigabytes of training data to people. I can actually use weights and biases to store that data and to send it to people instead of a tool like, say, Dropbox or Pastebin or other ways that people send data around. And the benefit here relative to some of those other tools is that data and models are kept close to one another and to any experiments you're running in this interface. So if you use weights and biases for your experiment tracking and for this versioning of models and data, then it's it's all in one unified spot. So maybe the question you might have is like, how much work is it to get all of this stuff? This seems like really great features, but how much work do I have to do to get this? So for if you're using a deep learning framework, so something like at a high level, something like Hugging Face or YOLO v5, we're integrated to a lot of the really popular frameworks. And so it doesn't take that much effort to get all of these benefits. So for example, with the YOLO v5 object detection framework, all you need to do is basically install weights and biases. And then once you've done that, you're ready to go. Just once the next time you run a YOLO v5 run, will all that information will be logged to weights and biases, and you can and you'll get those interactive dashboards. You'll get versioning of models and data. You'll get it all. Um, so we can see an example of that. This interactive demo here. So this collab uses YOLO v5 to train a raccoon detector, and tracks all the information with weights and biases. So that's this collab here. Let me restart it from the previous version of this demo. So the only thing that you'll need is a weights and biases account to log the information to. So that's these first two cells here. A little prompt will pop up if you're running this, sending you to a place where you can pick up your API key. If you don't have an account, that's where you would log in and create an account. But once once I've done that, and I'm logged into weights and biases, then all I need to do to run this YOLO v5 experiment, I don't need to. There's no additional code that needs to be written on the weights and biases side. Once the data is on the disk and I've got YOLO v5 installed, I just run it and I get this. I'll get a weights and biases workspace with all that fun information stored in it. So that's there's a cell there using artifacts. I happen to use artifacts to download this data set, but actually the data set was originally on RoboFlow, which is a sort of image labeling and annotation and sort of data set provision website. So I could have pulled it down from there. Just happened to be using weights and biases there. But so the core point I'm trying to get across here is that this is almost entirely code within the YOLO v5 ecosystem. So replace that with whatever high-level machine learning framework you might want to use, Hugging Face, PyTorch Lightning, Fast.ai, things like that. So when I run this cell here, I start up a training run with YOLO v5 and start training a model on the data that I downloaded. The data here is a bunch of pictures of raccoons that have had bounding boxes attached to them to identify where the raccoons are in the image. So let me pull up, let's see, this run. It'll take a second for it to get started. So let me just pull up what that overall workspace looks like. I've got a bunch of different runs here and how they've done on how they're doing on particular images. I can interact with that and see, I can move around and look at different how things develop during training. I can change here when you have a low, like when you're using one of these YOLO style object detectors, you get a lot of bounding boxes at those low object confidence scores. And if you just increase that threshold, we can clean that up and see how those highly confident boxes develop during training. Looks like they pop up a couple of epochs in. So we've got that rich information for that particular individual run that's currently running. I can dive in and look closer at it as it's going. There's some analyses built into YOLO v5 that are logged here, information about the labels and the bounding boxes. Then I can also see how those metrics are developing over time. And I've also got all that information that I showed you previously of what was the Git repo, and its status, and which command was used, and on which compute it was run. So all of that stuff with all that you need is an account and to install the library, and then you get all of that for free if you're using one of those high-level machine learning frameworks. So that's all I had for our agenda today. So one thing before I open the floor for Q&A in these last 5 minutes, I just want to say that we take really seriously the idea that we are part of the broader machine learning community. And so I invite you to like join us in our various community forums, our Twitter, our YouTube channel, our Slack channel, and to like help us build the tool that makes for the best responsible, reproducible ML and ML ops and sort of best practices for machine learning engineering. We get a ton of really helpful feedback from our users, and so we'd love to hear from you about what works for you, what doesn't work for you, and how we can unlock more value for you in your ML production pipelines. So with that, I'll open the floor to questions. If anybody has any questions about weights and biases and what how it works and what we can do for you. And you can put the questions in the chat window there in Hopin. As I wait for the any questions to come in, a great question that I got in the first session was, what do you think that there are the advantages of weights and biases over other similar platforms for experiment tracking and dataset and model versioning? And I think the biggest thing is actually on this last slide here, that weights and biases has this big sort of community of users in our Slack channel and on Twitter who are like uh, sort of just like working together on particular projects, sharing information, helping each other like debug their PyTorch code. We have a reading group that goes through papers. We have another one that's working through the Fast AI book. We have events and community driven initiatives that that mean that when you're working on projects with weights and biases, you're working with like a broader team of open ML of people interested in doing high quality, reproducible, open ML. And so I think that's a real big benefit of weights and biases. That's part of a conscious decision on our part to like build a community and give back to the broader ML community there. All right, I don't see any questions coming in the chat, but I definitely do encourage them in these last couple of minutes here. All right, well, I'll stick around just in case there are any questions in these last couple of minutes. But if not, I hope to catch you around out in the machine learning community and maybe see you in the weights and biases community sometime soon.